fact, since the current, well, it's a culture-based diagnosis that is used at the moment, and it takes approximately 2 or 3 days to detect some bacteria. So this promotes the widespread use of, well, broad-spectrum antibiotics and the emergence of multi-drug-resistant pathogens. In the world, this problem is becoming so serious that the World Health Organization has decided to put this as a center subject of the 2011 World Day, so it's pretty serious stuff. So what if we were able to reduce the diagnosis delay from a few days, say, to a few hours or even a few minutes? Well, I think that the answer to this question is quite obvious. What is less obvious is, of course, how to do it. Well, in order to achieve such a feat, some research groups approximately 15 years ago have suggested the use of whispering gallium resonators, and this is one. So dozens of papers have been published about this idea, and despite the improvement, well, this sensor is not yet used in the hospitals, so there's still a problem. My name is Vincent. I come from Université Laval in Quebec City, and today I will tell you about a project I made which concerns this issue. So I won't tell you so much about bacteria and urinary infection, but rather about the physics behind the idea, and I hope you can enjoy it and learn a little bit like I did. So the first question to address is, what is a whispering gallium? Well, we can start from a more familiar situation, let's say the propagation of light in a dielectric slab waveguide such as this one here. In such a waveguide, light propagates because of continuous total internal reflection on 2 different surfaces. So that means that we have 2 boundary conditions if we work in 2 dimensions. To each node inside the waveguide corresponds a specific trajectory, as you may have. And we may also notice the presence of evanescent waves next to the waveguide. And these waves do not carry energy, but they can act as a tunnel between the outside world and the waveguide itself. Now, if we bend the waveguide, what we notice is that the node trajectory will shift from the central axis to the external surface. And if we exceed this bending to a certain threshold, then we can expect that one of the 2 surfaces will become completely unnecessary. So we can simply remove the surface, close the waveguide in itself, and then we have a circle or a sphere. However, by removing one of the 2 boundaries, we've also lost the boundary condition. So to talk about a mode, well, we add the periodicity condition, which simply means that inside the sphere, we want to have constructive interference. And these spheres are not so complicated to make, actually. So this is one picture of one I made in 2011, after a few weeks of work. So it's quite straightforward. And because of this almost perfect reflectivity, well, we have a very good sensor that can store the light very efficiently. However, the reflectivity is not perfect, and it's very important because you can imagine by some symmetry arguments that if the light is perfectly stored inside the cavity, it's probably very difficult to get the light inside. So this brings us to the idea of coupling. How do we actually get the light inside? Well, one very simple and efficient way is to use another evanescent wave, so to rely on this tunneling property I told you about. And we can do this quite conveniently with a tapered fiber, which is illustrated here. So a tapered fiber is simply an optical fiber that was stretched under a flame so that it became very thin. So we simply bring the sphere close to this tapered fiber, plug one extremity of the fiber in a detector, the other extremity in a tunable laser, and when we scan the wavelength, what we notice are the modes. We measure the modes of the cavity, very simply. So why is this so exciting? Well, you can imagine that if we can store the light more efficiently inside the cavity, then that means that the light will go around for many, many round trips. So the interaction length with the outside world would be very great. And theory predicts that we should be able to detect single fibers with such a resonator. So what is illustrated here is the standard setup for this. So we have the tunable laser, tapered fiber detector, and what we detect when a virus gets close to the sphere is basically the wavelength shift of the resonance. Now you can track this shift like this and try to measure some parameters of what you're detecting with this. So, well, this is one of the 2 techniques. Well, I say 2, but there are actually many of them, but this is one of the simple techniques. You can also look at many modes at the same time and try to measure something else. In this case, this measure was done in my research group before I arrived, and they were able to detect bacteria on the sphere, but without any reference spectrum. So they just had a solution of freestanding spheres, and they are able, with the laser, to detect, to establish if there is something stuck in the sphere or not. All right, so now I'm going to introduce a new element, but I'll be back to the spheres in a few seconds. As physicists and engineers, we often like to summarize complex behaviors with a kind of black box or transfer function. Right, so this can give us the output of a system for a given input, and it's quite practical. But how do we do it in real life? How do we measure the transfer function? Well, I've just measured the impulse response of this disk, and this gives me a complete transfer function. So if I measure this sound you just heard, well, actually I'm characterizing the full system. So this can be quite easy in mechanics. Well, in optics, we just send a short light pulse in the cavity, and that's the same thing. How can you make a short light pulse? Well, with mode lock laser and a frequency comp, that's where it is, mode lock laser. So frequency in frequency, what I mean is the frequency comp in frequency is a train of pulses in time. So what we do is send a train of pulses in the cavity, and every time the pulse gets closer to the sphere, well, it will generate the impulse response. And thus, with some kind of complex system, we can measure the complete impulse response of the system and thus characterize it fully. So this is what it looks like here. When you do this, you have, it looks a bit complicated, but it's not so much. And, well, this is a very nice one, but suppose that's for a sphere of approximately 300 microns. So if we take the Fourier transform of the last plot I showed you, we get back to the frequency description, the mode description of the system. And this is a comparison. Here you have theory, here you have experiment with a CW laser, standard tunable laser, and here you have the frequency comp. And you can notice that there's a huge discrepancy between the theory and the experiment. The reason for this is that the sphere in real life is never perfect. There's always some distortion. And this gives us what we call degeneracy lifting, which you may have heard of in other fields of physics. So basically the modes all shift in different parts because it's not very spherical. Also, you can notice that both of these two plots here look quite the same, and you may ask, why do we do it if we get the same information? Well, it's a very practical idea. It's that using the frequency comp laser, we can actually measure the same answer, the same information, but 1,000 times faster. Because scanning the wavelength with a tunable laser can be quite long. It can take 20 seconds for this kind of bandwidth. But in this case, we can do it maybe 100 times every second, and we are actually getting it faster at the moment. So if you want to identify a bacteria, most bacteria are made of water, so they are not so different from each other. But if you are able to measure more parameters, let's say the shift of many modes at the same time, then maybe you can expect to be able to differentiate these bacteria. So that's the basic idea. Now that you have a good grasp of the physics behind this project, well, let's look at some results. This is a refractive index sensing experiment. So basically, you have a sample cell filled with water, and you just inject isopropyl alcohol to increase the refractive index. When we do this, well, we can notice this is the impulse response. This is the first pulse that gets through the tapered fiber but doesn't interact with the cavity, so basically goes straight through. And this is the second pulse, which is the one that goes for only one round trip into the cavity. And there are a few interesting things to notice. Well, first of all, the faint trace here is the magnitude, and the bright trace here is the real part. So magnitude is changing slightly when we increase the isopropyl concentration because, well, isopropyl alcohol is slightly more absorbing than water. So we are increasing the absorption. However, the group velocity is not changing, as we noticed, because the pulse position in time is not changing. If we take a look at the real part,